Ever wondered how to guarantee your MCP client properly initializes, connects, and cleans up without writing a single line of manual connection code? We'll implement the standard FastMCP pattern that handles everything automatically: connection establishment, protocol initialization with capability exchange, and proper teardown, all through a single async with block. You'll see how the context manager not only manages the connection lifecycle, but also performs the MCP initialization handshake, making server metadata and capabilities immediately available for your operations.
Async def example. Client equals client, my MCP server, pi. Hash connection established here. Async with client. Print f connected, client is connected. Hash make multiple calls within the same session. Tools equals await client list tools. Result equals await client, call tool, greet. Name, world. Hash connection closed automatically here. Print f connected, client is connected.
This demonstrates the context manager pattern for both connection lifecycle and protocol initialization in MCP clients. The approach uses async with to encapsulate not just connection establishment and teardown, but also the automatic MCP initialization handshake that exchanges capabilities and server metadata. The distinctive aspect is how it combines infrastructure management with protocol initialization while keeping all operations explicitly controlled by the developer. The pattern works by deferring all connection activity and initialization until context entry. When the async with block begins, the client automatically establishes the connection, performs the MCP handshake to exchange server capabilities, and makes the results available via initialize result. All operations must occur within this managed scope, ensuring proper cleanup when exiting, including both connection termination and initialization state reset. This creates a clear separation where the framework handles protocol concerns automatically, but never makes implicit decisions about which operations to execute. This approach solves three critical problems: connection leaks, incomplete initialization, and ambiguous state transitions. It's particularly valuable for MCP interactions where proper initialization and capability exchange are prerequisites for any operation. The trade-off is that all MCP interactions must occur within the context block, but this constraint guarantees deterministic behavior and prevents resource leaks. For advanced cases, the pattern supports manual initialization control while maintaining the same safety guarantees. Let's break it down line by line.
Async def example.
Declares an async function, required for all FastMCP operations since the client uses async networking. The async def enables non-blocking I/O calls to the MCP server, allowing concurrent operations while waiting for responses. This matches FastMCP's async-first design, where all tool calls and connection management must be awaitable.
Client equals client, my MCP server, pi.
Creates a client instance targeting the server defined in my MCP server, pi, but does not establish any connection yet. This is purely endpoint configuration. The actual connection, initialization handshake, and capability exchange only occur when entering the async with block. The pattern combines connection lifecycle management with automatic MCP protocol initialization.
Hash connection established here. Async with client.
The async with block handles both connection establishment and MCP initialization. When entering the context, FastMCP automatically performs the connection handshake and capability exchange, making server metadata available via initialize result. This pattern ensures proper cleanup of both connection and initialization state when exiting the block, preventing resource leaks.
Print f connected, client is connected.
This checks connection status after the context manager automatically handles both connection establishment and MCP initialization handshake. The async with block triggers the full initialization sequence, including capability exchange and server metadata retrieval, before any operations execute, with results available via client initialize result. Critical for verifying the context manager properly completed both connection and initialization phases.
Hash make multiple calls within the same session. Tools equals await client list tools.
This fetches the available tools from the MCP server after the context manager has established the connection and completed initialization. The await ensures non-blocking execution while maintaining session state, allowing subsequent tool calls like call tool to operate within the same initialized connection. The list tools call retrieves the server's capability manifest, which includes all callable tools and their schemas.
Result equals await client, call tool, greet. Name, world.
This executes the greet tool remotely with parameterized input, passing arguments as a dictionary. The await suspends execution until the server processes the call and returns a structured result, demonstrating FastMCP's standardized tool invocation pattern, where all parameters are serialized as JSON-compatible types. This matches the protocol's design, where tools expose clean interfaces while handling all serialization internally.
Hash connection closed automatically here. Printf connected. Client is connected.
This confirms the connection is properly terminated after the context manager exits. The async with block handles both connection establishment and MCP initialization handshake when entered, then automatic cleanup when exited. The pattern ensures complete lifecycle management, connection, initialization, and teardown in a deterministic way. FastMCP initialization pattern. The async context manager handles both connection establishment and MCP initialization automatically, performing capability exchange and server metadata retrieval when entering the context block. All operations must complete within the async with scope, as the connection and initialization state become invalid immediately after exit. This pattern ensures deterministic resource management while abstracting away protocol handshakes.
The client that connects without connecting first becomes the most connected client.